Hello, this is Dr. Baxley. This is a lecture video for Chapter 4. This is going to be Part 1, the stoichiometry portion. There will be at least 3 parts to Chapter 4, maybe 4 parts. Just trying to keep the videos a little shorter and not quite so long. The first part of Chapter 4 is all about reaction stoichiometry, or in plain English, it's the ratio or amounts of one chemical substance related to other chemical substances. In order to do stoichiometry, we have to know the balanced chemical equation for a chemical reaction, and those number ratios of one substance to another. Those are the coefficients in a chemical reaction. In the coefficients, those will tell us the number of moles for each substance relative to other substances. For example, in a chemical equation of methane reacting with oxygen molecules, we can see that there's one molecule of methane that will combine with 2 molecules of oxygen in order to form the products. 1 molecule of CO2 and 2 molecules of water. We can also use those in terms of moles as well. So one could say that there was 1 mole of methane that would combine with 2 moles of oxygen. Here's a concept question for stoichiometry, or relating chemical amounts of one substance to another. Here we have a chemical reaction with 4 moles of sodium combining with 1 mole of O2 to make 2 moles of sodium oxide. Take a moment, pause the video, and try to determine what the correct amount of sodium is needed to react with all of the oxygen gas. Hopefully you've got the correct answer now. We can determine the correct answer by using stoichiometry. Using the 3 moles of oxygen gas given to start with. That value can be multiplied by a mole-to-mole ratio from the chemical equation. There are 4 moles of sodium and an implicit 1 mole of oxygen gas needed to react with it. 3 moles of oxygen times 4 moles of Na for every 1 mole of O2. The moles of O2 reduce to 1 and cancel out, yielding 12 moles of Na. C would be the correct answer. Here are a couple of YouTube videos to watch. I urge you to watch the Edpuzzle version of the video. Go ahead and watch that now and see what you see. It's kind of fun. It's only 3 minutes. So what's stoichiometry good for? Well, what's more useful and fun than debunking stuff you see on the internet? In the video that you watched, you might have seen 2 pause points. In one pause point, the narrator of the video says, and you can almost hear the air quotes, "Science" for Brainiac. In the second stoppage point, you might see a wire that runs into the bathtub. Why would anyone need a wire that goes into the bathtub? Well, you need a wire that goes into the bathtub if you put dynamite in the bathtub. Yes, that's right. That video was faked. They used a 1/4 stick of dynamite in the first reaction to blow up the bathtub and a 1/2 stick of dynamite in the second reaction. It was very sad. In order to debunk the internet myth, we can look at how much hydrogen gas forms from each of the metals that was involved. We'll start with lithium. We can calculate the number of moles of hydrogen created with the reaction of 2 grams of lithium, because the Brainiac video says they started with 2 grams of the rubidium and cesium. Starting with the 2.00 grams of lithium, we need to convert that to moles so we can use the mole-to-mole ratio from the chemical equation. From the periodic table, we can see that 1 mole of lithium is equal to 6.941 grams. From the chemical equation, the mole ratio of lithium to hydrogen can be seen as 1 mole of hydrogen for every 2 moles of lithium. This turns out to be 0.144 moles of H2 that are possible from the lithium metal. We can do the same thing for cesium, starting with 2.00 grams of cesium. The chemical reaction is just the same, substituting cesium for the lithium atoms. In this case, 1 mole of cesium is equivalent to 132.91 grams. The mole-to-mole ratio is the same. And this works out to be 0.00752 moles of hydrogen gas from the cesium. You can see that the amount of lithium that was used makes a lot more hydrogen gas than the cesium metal can make. And it's the hydrogen gas that's important in the reaction. The hydrogen gas reacts with oxygen to make water, and that's really what the explosive power of these reactions are. You can see then that the amount of hydrogen from cesium being so much less than lithium wouldn't really blow a bathtub like they showed in the Brainiac video. Totally sad. It was the first fake news I ever encountered. The last question was a question where there was a fixed amount of one reactant and lots of the other reactant, 2 grams of a metal in a bathtub full of water. But what if one or more of the reactants had fixed amounts? In that particular case or situation, we run into a type of problem that's called a limiting problem or a limiting reactant problem, where it's likely that one of the reactants will limit how much product can be made. We're going to look at this particular scenario where 10 grams of hydrogen gas reacts with 20 grams of oxygen gas to make liquid water. Before we do any kind of chemical calculation problems, it's super important to have a balanced chemical equation. In fact, anytime you come across a chemical problem in this class, you should try to write a balanced chemical equation. So pause the video, take a moment, and try to write a balanced chemical equation. We would start with the H for hydrogen. Because H is one of those diatomic elements, we'll write H2, and we'll use G for the gas phase in parentheses. We'll add that to oxygen, also a diatomic element, and make H2O liquid. In order to balance this particular reaction, we can see there are 2 hydrogens in the reactants and 2 hydrogens in the products. Those look balanced. There are 2 oxygens in the reactants, but only 1 oxygen in the products. There needs to be a coefficient of 2 out in front of the water then. Well, of course, that changes the number of hydrogens to 4 in the products, needing a 2 in front of the hydrogens in the reactants. Here's a picture of the Hindenburg. That was a big blimp filled with hydrogen gas. It caught fire back in the 1930s. It's exactly the kind of reaction that hydrogen does in the presence of oxygen. We can now calculate the theoretical yield, or the maximum possible mass, of water that can form from those 2 amounts of the reactants. Starting from 10.0 grams of hydrogen, in order to use the stoichiometric ratios from the chemical equation, the mass of hydrogen needs to be converted to moles. From the periodic table, we can tell that every mole of H2 would have a mass of 2.02 grams. Don't forget, I always encourage students to use 2 decimal places for all their molar masses. Once the number of moles has been calculated, then it's up to the chemical equation to show the relationship between the reactant we're discussing and the product we're looking for. In this case, it's a 2-to-2 ratio. So for every 2 moles of H2 used, 2 moles of H2O will form. Once the mass of H2O is known, then that mass can be converted to moles using the molar mass from the periodic table. And that works out to be 89.2 grams of H2O, and that's the possible amount from H2. The same set of steps can be repeated for oxygen. 20 grams of oxygen multiplied by its molar mass multiplied by its mole-to-mole ratio. From the balanced chemical equation, the coefficient of the oxygen is implicitly known to be 1, and the coefficient for water is still 2. So for every 1 mole of oxygen consumed, 2 moles of H2O would form. And then once the number of moles is known, that can be converted to mass of water, just like before. And that calculation yields 22.5 grams of H2O. That's possible from the oxygen gas. To answer the next set of questions, we know the balanced chemical equation. We know the possible masses from both reactants, the 89.2 grams that we could get from the hydrogen and the 22.5 grams that we could get from oxygen. Once the 22.5 grams of water have formed, the oxygen has been completely used up. We can't make any more water. That means that this mass, the 22.5 grams, is the maximum possible mass of water. It's kind of weird. It's the lower number, but it's the biggest one possible. The reaction couldn't produce the 89 grams of water because there's no more oxygen present. It's done. We would consider in this case the limiting reactant to be, I'll let you take a guess. Hopefully you got it right. The limiting reactant is the O2. Because the oxygen runs out, it prevents the reaction from forming more product. Now in many chemical reactions, just like when you're cooking at home, the mass of the product might not end up being the theoretical mass. For example, when you bake chocolate chip cookies at home, no one ever gets 48 cookies like the directions say you will. Lots of different things can happen. You can lose some product in the reaction container. Some can stick to the walls of the flask or the bowl in the case of the chocolate chip cookie dough. Sometimes there are side reactions. Sometimes something comes in and gobbles up some of the reactant, like the cookie dough. Lots of different reasons to lower the actual yield of a reaction. So in this particular case, if for some reason only 12.5 grams of water were recovered, one could calculate the percent yield for this reaction. Simply take the 12.5 grams obtained and divide it by the 22.5 grams that's maximum or theoretically possible. Multiply that by 100%, and that works out to be 55.6% in terms of the yield. In real chemical reactions, really dreadful ones, sometimes you end up with a percent yield of maybe 10 to 20%. Those are not very fun reactions to do. There's a nice little figure in the text that kind of shows the process for solving a limiting reactant type of problem, or any stoichiometry problem in general. If you have mass of the substance to start with, the mass needs to be converted to moles, using the molar mass of that particular substance. Then the number of moles of that substance can be related by the coefficients from the reaction, or the balanced equation, to relate moles of substance A to moles of substance B, just like we just did with H2 to H2O. And then if one needs to calculate the mass of the product, substance B, then one could use the molar mass of B to convert moles back to grams. There's another little figure in your text, so if you're reading Tro, you might come across this figure. The author of our textbook suggests that you stop and calculate just the moles of the product possible from each of the two reactants. Here would be reactant 1, here's reactant 2. What I showed you in the previous examples was to calculate the mass of the product from each reactant. Either method works. This involves one step with the molar mass of the product. My method involves doing that twice. It's not a lot of extra work. Like I said, either method could work, whatever you decide you're comfortable with. Here's another little figure if you like more of the cartoon issue. One can calculate from the mass of a reactant or some other substance, like a product. So from reactant or product, you can calculate moles with the mass to mole ratio. Once you know the number of moles of the substance that you just worked with can be related to the moles of some other substance. So you can do reactant to reactant. You can do reactant to a product. You could do product to a product. Or you could do a product to a different reactant. You can change lanes almost, once you know moles, using that mole ratio from the balanced chemical equation. Once you know the moles of another substance, you can convert that to mass using the molar mass. I had some students a few years ago that showed me this kind of diagram that they came up with, and they called it the mole highway. You can get on the mole highway with grams to moles, you can get off the mole highway with grams to moles, and you can change lanes with the mole ratio from the balanced chemical equation. It's kind of corny, but I like it. Here's some tips for solving stoichiometry problems. Make sure you figure out what the question is. Read it a couple times, make a note. I'm looking for mass of something, or moles of something else. Always make sure you have a balanced chemical equation. Sometimes it helps to draw a picture too. If the particular problem is kind of complicated, lots of moving parts, draw a little sketch or a diagram to show what happens from part A to part B to part C. You have to use the number ratios, the stoichiometric ratios from the balanced chemical equation, to compare a product to a reactant or any other thing. But make sure you use number ratios, moles, not mass ratios. Sometimes it helps to look at the problem from both ends. It helps you figure out where to start, and it might help you figure out where to finish. And I also encourage students not to fall into a problem trance. It's really easy to have the pattern from the last slide. Go from mass, use molar mass, calculate moles, use mole ratio, use molar mass again. It's really easy to fall into a trance with that kind of problem-solving technique, but you never know, there could be a twist in the problem. You might have to do something slightly different. So make sure you think. Don't sleepwalk through a problem. There's also an interesting thing that some students get hung up on, and that's how much is present versus how much reacts. The how much it reacts part is the chemical equation. That's the mole-to-mole ratio from reactant to product. And it's kind of like a recipe for baking chocolate chip cookies. In the recipe for chocolate chip cookies, you know it's always 3 cups of flour to 2 eggs. Now you rarely in your kitchen at home have exactly 3 cups of flour and 2 eggs. You might have 10 cups of flour, or you might have a dozen eggs. That is the how much is present. That's the starting amount. And the starting amounts aren't necessarily equal to the amounts required in the chemical reaction. So just keep that in mind. They need to be separate items. Here's another practice problem dealing with hydrazine, which is used as a rocket fuel, and hydrogen peroxide, H2O2. I got the inspiration for this problem from The Martian, one of my favorite books that I've read in the last few years. First, see if you can follow these steps without looking at the solution below. You'll need a balanced chemical equation, of course, because you know you're supposed to do that for every chemical problem now. See if you can determine the maximum mass of HNO3 that would be formed. See if you can figure out the limiting reactant. See if you can figure out the mass of the reactant in excess that's left over. Here's a little picture of the book, The Martian. It's a great book. I highly encourage you read it. Going back to this last question, what mass of the reactant in excess is left over? Let's say you're doing some cooking at home and you're making chocolate chip cookies, and you've used the 3 cups of flour, and you've used 2 eggs, and someone wants you to figure out how many eggs you have left. Well, with eggs you could just count them, but with chemicals you can't. So another way to figure out how many eggs are left is to figure out how much you had to start with, subtract from that how many you used, and that would equal how much is left. Go ahead and get started on that problem, but again, don't cheat. See if you can work it out on your own and then check the answers. So pause the video and get to work. All right, you've paused the video, you've gotten to work. You've figured out that you can make 195.6 grams of nitric acid from the hydrazine and 105.8 grams of the nitric acid from the hydrogen peroxide. This is the most you can form, meaning that hydrogen peroxide is the limiting reactant. What do you do about the reactant in excess that's left over? Well, you know that all 200.0 grams of the hydrogen peroxide gets used up in the reaction. It's the limiting reactant, it's used up. So one can take the starting amount of the hydrogen peroxide, calculate moles of hydrogen peroxide, and then instead of looking at the product, we can look at the other reactant, the hydrazine. From the balanced chemical equation, one can see that it takes 7 moles of H2O2 to make 1 mole, to use 7 moles of H2O2, it would also use only 1 mole of N2H4. So at this step here, this would be moles of the other reactant that would be used. If we know moles of reactant used, we can calculate the mass with the molar mass of the hydrazine, and that would tell us that the 26.92 grams of N2H4 were used up. We know we started with 50 grams. We can subtract the 26.92 and find out that there's 23.08 grams of N2H4 that are left over after the reaction's complete. Does this number make sense? Well, let's look back at the possible amounts of products that were potentially available for the two reactants. From the H2O2, we could only make about 100 grams of the HNO3. From the hydrazine, N2H4, we could make almost 200 grams of the nitric acid. That's almost twice as much possible from the hydrazine reactant. So it seems like maybe we only used half of it to get to about 100 grams. And sure enough, about half of the hydrazine was used, about 27 grams, leaving about 23 grams left over. So it's kind of nice that number makes sense for us. Here's another practice problem. This one asks about nitrogen monoxide being prepared by oxidation of ammonia to make nitrogen monoxide and water. In order to oxidize ammonia, one needs another reactant. In order to oxidize something, O2 is often used. And so O2 is the other reactant in this particular reaction. So pause the video, see if you can follow the same sort of steps to calculate the theoretical yield of NO, the limiting reactant, the mass in excess for the excess reactant, and the percent yield if the actual yield was a mere 35.3 grams. The answer to the questions is on the next slide. Here you go. Here are the answers. First of all, one has to have a balanced chemical equation. There were two possible amounts of NO formed, 39.4 grams from O2 and 80.5 grams from ammonia. Of course, the 39.4 grams is the most we can make. At that point, all the O2 runs out, so O2 is the limiting reactant. In order to figure out how much of the excess reactant is unreacted, we can follow the bottom calculation. We know the O2 is the limiting reactant, so it gets used up. We can calculate the number of moles of O2 that were used, the number of moles of ammonia needed to react with that much O2, calculate the mass of that much ammonia to find out that 22.4 grams of ammonia were used. Subtract the 22.4 grams that were used up from the 45.7 grams to start with, and it turns out there are 23.3 grams of ammonia left over. So that's a pretty good introduction to stoichiometry. I hope you've enjoyed the video. Let me know about some feedback. I don't often watch these things all the way through, so if there's a bad spot, maybe I can edit it. If something really worked well, let me know. If it didn't work well, let me know. Thank you.